Very good. All right, so purposely. So I apologize, I meant to send the solutions. I'll do that right after class. The average grade on the exam was 81%. In any event, well, you have your temporary grade, and so think about it. The oral exam will be next week, and those of you who want to do that can talk to me about it before if you want to think about it. And we'll find a time of our mutual convenience. Yeah?
The temporary works that if we don't do that, we don't do the oral final, we don't do the extra homework, that becomes our grade, right?
That's correct. Yeah. So that the temporary grade there is your grade based on the information I have right now. And if you, so it will be modified based on the homework assignment that's due today. And I'll let you know that once we have that graded. Probably won't change any grade. The extra credit homework. They could.
The final could?
What?
The final can change your grade?
Yes, certainly that could. In a big way. Either direction. It will be added in as a third exam based on the percentage. So right now, the way the grade was calculated, basically 1/3 of your grade was homework, 1/3 of the grade was the first test, and 1/3 of the grade was the second test. And so if you elect to take the final exam, which will be cumulative over all the material, not including this material, but the material including homework assignment 11, then that will count, the homework grade will be 33%, and each exam would then be 20-something%. All right? Okay. Let's see. So also we'll discuss at the end of lecture today whether we all have the stomach for more lectures. Speaking of having the stomach for anything, more teaching, more learning, one topic that we didn't get to that's very important is scattering theory. So I might be willing over the summer to do a little mini course for anyone who's interested over the month of July. Maybe one day a week to cover that material. So if you're interested, let me know, and I'll think about it. Yeah?
I'm assuming there's no prom session tomorrow, right? Or
There's no problem session tomorrow. No.
There's no problem tomorrow.
just make sure it wasn't going to be a bonus lecture or something.
All right. Very good. So last time we were talking about this formalism that's known as second quantization. Now, the term second quantization is somewhat mysterious. There's lying in the world, we call it second quantization. We'll get to that, wherever that term comes from. It's a somewhat arcane term, and it's somewhat misleading. But I'll explain why that language still exists. Okay. So, but the basic idea, the basic point here is that we are looking at the quantum description of many body systems where we have some collection of identical particles. Okay? And each of those particles is described by states in some Hilbert space. Okay? So we have each particle is, if we had an individual of such particles, there would be a Hilbert space. I'm calling it little h, and there's some states in that space, the Hilbert space with some inner product in the usual way. Okay? And what we've discussed up to this week is when we're talking about collection of identical particles, then we can't just look at the tensor product of each degree of freedom associated with each particle. We have to look at the subspace of that space that is restricted to either the completely symmetric under exchange of any two particles or completely anti-symmetric under the exchange of any two particle spaces. Okay? And so, for example, if we had a two-particle system, then, states in that system we have to explicitly write out, there's particle 1 can be in this state or particle 2 can be in that state, and then it doesn't really matter which is particle 1 or particle 2 because they're identical, and we have to appropriately symmetrize or anti-symmetrize. And the same for operators. If we had some operator that's acting on the one particle and another operator on the other particle, we don't know which particle is which, we have to symmetrize. Okay? All right, and that's a somewhat awkward construction. And a much more elegant and useful way of dealing with many body physics is to think about second quantization. Okay? So in second quantization, the star of the show is Fock space. And Fock space is a Hilbert space. It's the Hilbert space of my many body system. And generally speaking, when we talk about a Fock space, typically we're thinking about some not necessarily a definite number of particles. So we allow for some possible different numbers of particles in the system. And we might, if we want to, though it's not necessary, to say there's some maximum possible number of particles that we're going to deal with. And so it's the direct sum of the Hilbert spaces associated with some number of particles n. And the way we can think about that, there's many ways to think about it. So if I have some, again, each one of these particles inherits the structure associated with Hilbert space H, little h, and that we might say some d-dimensional Hilbert space. It could be infinite. We'll come back to that in a little bit. So a basis for the space of the Fock space associated with n particles is given by the span, or the basis are these states. That is to say, these are states with n sub I particles in the state E sub I. So I have n particles and I put them in D boxes. And I do that according to either what's allowed if they're bosons or fermions. If they're fermions, then these are either 0 or 1, because we cannot have more than one particle in a state, assuming this state specifies all the quantum numbers, right? Right, so the important state in the Fock space is the so-called vacuum state. This is the one state in this Hilbert space with no particles at all, okay, up to overall phase. And we define this new structure of creation and annihilation operators that act on states in the Fock space. And so to each state in our single body Hilbert space, we can assign to any state in that space, we can assign a creation and annihilation operator, which has the property that if I operate this creation operator on the vacuum, I get the equivalent one body state in the Fock space, with one particle in that state. Okay? So what we discussed last time is that the structure of exchange symmetry imposes relations on the creation annihilation operators. If they're bosons, then it's symmetric under exchange. Okay? Sorry, there shouldn't be a tag in here. So I can exchange them and I get the same thing back. Symmetric under exchange. What that says is that all of the annihilation operators commute with one another, and all of the creation operators commute with one another, no matter what the state is. But the creation and annihilation of operators don't commute with one another necessarily, unless they correspond to orthogonal states. So the commutator of A with annihilating that state with the creation limited to that state is this. I love this formulation of the problem because it's basis independent. Okay, it says nothing about, typically this is written down in a kind of basis dependent way. This is a much more elegant formalism. It's the way Professor Dickmann taught me in Berkeley, and he was great. This is the way I learned it. Right. In contrast, the fermions are anti-symmetric under exchange. So, and that makes them a pain to deal with. And I screwed it up last lecture because I never deal with fermions in my own work to practice with it. But it's a pain. You have to learn how to do it if you're going to do it. So what it means, every time you switch the order, you have to put a minus sign. Okay? So that means that we don't define their commutation relations, we define their anti-commutation relations, okay? The anti-commutator is the number written in a different order with the plus sign rather than the minus sign, okay? And this says that annihilation operators all anti-commute with one another, and all creation operators anti-commute with one another. And we don't say anything about what their commutation relations. We have to do the commutations by hand based on anti-commutations, and I'll show you an example of that in a moment. And the anti-commutator between the creation and annihilation operator, again, is a set of product. Okay? So, often there is some basis that we want to think about of single particle states. So quite often, there is some basis that we want to analyze the problem in, basis of single particle states. And we'll just label them by whichever basis state that is, okay? And so written in this manner, for the bosons, what we see is that all the, the creation operators or annihilation operators, they all commute with one another for all the basis states. But the creation and annihilation operator associated with two basis states, that is, as always, equal to the inner product of the states associated with that. And in this case, this is an orthonormal basis, and so that commutation relation is the Kronecker delta. Okay, so that says that creation annihilation operators associated with different basis states, they commute. But for the same basis, the commutator is 1. All right? And we recognize these commutation relations as those associated with a collection of D independent simple harmonic oscillators, right? So if I had, n masses on a spring, each one distinguishable, this would be their commutation relations. So that's why often we call the commutation relations associated with a collection of harmonic oscillators the boson commutation relations, or the boson algebra, even though we might not even be thinking about identical particles. Okay.
In that relation, D is the number of
basis states.
Of the simple harmonic oscillator.
No. It's the number of simple harmonic oscillators.
Yeah.
Each simple harmonic oscillator has its own set of creation operators, and I can have some number of excitations in that. And the number of excitations is the number of particles.
Yeah, that's what I was trying to say.
Yeah.
Okay.
So the number of particles, D has nothing to do with
The dimension.
the dimension, it's the number of oscillators.
Yeah, exactly.
In this case. Yeah.
So, yeah, exactly.
Okay, good. And furthermore, there is this important operator, the number operator, which we know from our studies of simple harmonic oscillator, and very easy to show that they satisfy these commutation relations, and from that we easily see that the action of the creation annihilation operators on these Fock states act to add or subtract a particle from that state, and there's the appropriate normalization that happens, right? And so in the case of bosons, we wrote this as a way of writing this Fock state as the action of a set of creation operators on the vacuum raised to the power of the number of particles. And we have this generalization we're going to come back to in a moment, which you easily see. Now what about for fermions? And this is where I kind of messed it up a little bit last time. Well, for fermions, we have the anti-commutation relations. Bless you. Right. And of course, one thing we see from this automatically is that this is equal to 0. That is a statement of the Pauli exclusion principle. Okay? What about, so now let's ask about this operator, n sub I. These are fermions. Okay? Now I ask you, I should have asked myself, but now I'll ask you, what is the commutation of n sub I with a dagger? Well, we don't know how to do the commutators because they're not defined, but we know how to do the anti-commutators. That's not what I meant to say, but it says this. Okay, because we need that example, right, to ask the question. I should have said, of course, what's important here is this means that n sub I eigenstate, right, with eigenvalue n sub I, right? Then that follows from this. All right. So now, how are we going to do this?
But why the commutation is 0?
No, it's not 0, actually. Sorry, because I'm not paying attention to what I'm thinking. So what I meant to say is question. It's not 0. How are we going to do it? Well, we could just write it out. This is a dagger A. So the commutator n sub I with that dagger is equal to that, right? Minus that. That's just writing out the commutator. That's still true. I just wrote it as n times this minus this times n. Yep.
So is the AI squared equals 0 equal AI dagger squared equals 0?
Sure, that must be true, because if I dagger both sides of the equation, then this is also true, right? So that's nice. So this is 0. Okay. What about this? Well, I know how to anti-commute this thing. So this is equal to, I write it in the opposite order, but I have to put a minus sign, and then I add the anti-commutator to it. Okay? Do you see what I did? Every time I switch it, I put a minus sign and I add the anti-commutator. Because then this plus this is 1. Okay? Now what? This is 0, because a dagger squared is 0. And I get the same commutation relations that I had for bosons, which I must, because this is also the number operator for fermions. Okay? So I did it in a kind of cockamamie way last lecture, but this is the general. And you can, so this means again for fermions that this is an eigenstate, and of course this is either 0 or 1. That's all it can possibly be, but it's still a number operator for fermions as well. And generally, you can say that this is true, we'll come back to this in a moment, that AI dagger AJ with a K dagger for fermions as well, doing the same thing, is equal to AI dagger delta JK. So this is just stupid. It's not stupid, but it's not what I meant to write. It's true. I think I want to use it a little bit. All right. So this was the definition of states. Oh, I guess there's one thing I wanted to say about states, which is, so one of the things we saw was that if I had some state in my single particle Hilbert space that is a superposition of calculates that if I look at the creating operating that state, that is just a linear combination with the same superposition of creating. It's got exactly the same structure. Right? Yeah, that's correct. That's not true for the annihilation operators. They've got to have stars on bars over there. Okay? So, one thing you can ask, so we wrote down a Fock state, a state with definite numbers of particles, in terms of particular basis. But maybe I want to change the basis. Okay? So let's let, say, f sub I equals 1 to be another basis. For my single body Hilbert space. Okay. So we know from all the quantum mechanics we've been doing that if I wanted to say look at the J guy, I could always write it in terms of bless you again. The original basis by just inserting complete set, right? And this is the unitary. These are the elements of a unitary matrix that performs a similarity transformation that takes me from this basis to that. Right? So similarly, let V sub j be the creation operators associated with these basis elements, okay? A sub I are going to be the creation operators associated with the other basis. Okay. So now I can relate this by exactly the same, by this argument that I just made, that these creation operators are equal to superpositions of the other operators, right? So they are EI Fj creation to be, right? Or equivalently, the annihilation operator Bj is Fj EI. So, for example, this is to say that, generally speaking, if I had a state which is as a Fock state with, say, some number of particles in some basis states, with respect to another basis, it's a superposition. So, for example, if I have the state, let me get some better shot. So this creates one particle in the state F sub 1, right? Now that is a superposition of creates, not annihilates, pardon me. This is the state that would say sum over all E sub I F1s A dagger I, right? So this state would have an amplitude E1 F1 1 0 0 0 0 plus E2 F1 0, 1, and state 2, plus dot, 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 e sub d, f1, 0, 0, dot, 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 one particle in the B state, where these are a priori decided to be the canonical basis, or the fiducial basis, or the computational basis, whatever basis I want to call it, that defines the order of the E sub i's. So this is one state in E1, in E2, E sub D. Okay? So typically you would decide what are the sort of the, what's the standard basis, and we talk about some number of particles in that basis. But this is an eigenstate of the number operator. What is his eigenvalue?
0 to 1, depending on the number operator, right?
The operator is the operator. Here's a state.
Sum of later product.
So let me call this state. Okay. Now, I ask the number operator is the sum over all states in sub I, right? That's the total number operator. And now I claim that this state is an eigenstate of the number operator with some eigenvalue.
And,
What is its eigenvalue?
and? Well, because all
I claim it's a number 1, 2, 3, 4, and 5.
1.
It's 1. This is a one particle state. It is an eigenstate of the number operator with eigenvalue 1. It has one particle. Now it's true. I don't know if with respect to this basis, I don't know what state the particle is in. The particle could be in E1. It has this probability amplitude. It could be in state E2. It has this probability amplitude, blah, blah, blah. But it is one particle, and only one particle. There's no uncertainty in the number of particles. It is an eigenstate of the number operator with eigenvalue 1. Now, we also know, if I wanted to, it is the one particle in the state F1. Right? I mean, it's obvious here that it's a one particle state, because I just created one particle. So it's just a point I want to emphasize about it doesn't matter what basis I use, this is a one particle state. Now, each one of these states has exactly one particle in it. I just don't know which state it's in with respect to the E sub I basis. Okay? Now, there's also a little bit of strangeness here, this question about entanglement. See, if I wanted to think about this as a tensor product of different harmonic oscillators, say, these were bosons, then this state looks like an entangled state, because it's not a product state, it's a superposition of product states. But do we really want to call this thing an entangled state? I mean, all I did is I just created one particle, I just changed the basis. Well, there's a lot of subtlety associated with that question. It really has to do with the question, does it even make sense to think about these guys as independent commuting subsystems? Only then can I really talk about isolating one subsystem, tracing out the rest, and asking about entanglement. If these were bosons and I allowed myself an arbitrary number of particles, then in some sense this is entangled. But it's entangled with respect to the modes. Something sort of subtle. We'll come back to maybe. All right. Next, we were talking about operators. Let's see. So, what we had to think about in the first quantization language well, if I had some operator or observable, if I want, if this is a case of a Hermitian, I'll use a little O for observable. Let's say I have a one body operator, O, on H. Then if I have a basis, some particular basis, then we know we can always write a representation of that by inserting the resolutions of the identity. That's nothing more than the matrix representation of the operator with respect to the basis, right? So now I promote this, move the tassel, to the Fock space. So now it's a many body space, but this operator only acts on one body at a time. And we can do that by the construction so now wherever I saw this cat, I create or this is just a number, it doesn't matter what. I write it O-I-J, A-I-J. You could see that that must be, or this is correct, by asking, does it get all the matrix elements right now on the Fock space? Okay? So let's say I have a single body state psi, which is the creation of a particle in the state psi acting on the vacuum. Okay? And let phi be the creation of the state phi in the vacuum. Right? So now let me calculate the matrix element like that. Okay. Well, let's make one of these phi. So this is equal to the sum over ij O-I-J A-I dagger A-J, and then I create a particle in the state phi. Right? So I just plug in. This is my operator, and so this is my state. And this is the O. All right? So now this is equal, it's all linear still, so sum over I and j, the vacuum expectation value of that. Right? Okay, so now what? Now here's the standard kind of tricks you play when dealing with this kind of Fock space. What we know is that the annihilation operator annihilates the vacuum. So if I can switch the order, then I just have to have the term that's majority because this the first one kills it, right? And similarly, here, if the creation operator acting on the bra version of the vacuum annihilates the bra version of the vacuum. So I just have to switch the order and replace it by the commutator or the anti-commutator, right? So this, I claim, is equal to the sum over I and j, the vacuum expectation value, and I'll use the notation here, plus or minus to meaning either commutator or anti-commutator, okay? By the reason we just discussed. Because the other term, when you flip it, annihilates it. Okay? Plus or minus. Okay, so now what is this? For either boson, if it's a commutator for bosons and anti-commutator for fermions. It's a commutator or anti-commutator with A and A dagger.
It's the delta function.
It's kind of like the delta function, but not exactly. The general rule is written over there. Right, it's the inner product, right? And what inner product is this?
Sine of E sub I.
Sine of E sub I. Right? And what is this?
Phi of E sub J.
Yeah, and E sub j is first.
Yeah.
And then, oh, I forgot, what happened to the OIJ? I left it out. OIJ. Okay. Excellent. So, what we see is that this matrix element calculated with respect to this Fock space is this. E is psi E I O I J right? And what's that? Well, that's just, this is the matrix, this is the rows and columns, column vectors. This is just yay. So it's a nice formalism. It works nice. Yeah.
If we have a state that lives in H2, an eigenstates of number of particle 2, then any expectation value of one body operator on this state would be 0?
No.
Okay.
Not necessarily. So it really would depend. I mean, so this operator is not restricted. I mean, this is an operator on the Fock space, and I can take its expectation value with respect to any state, which might not have exactly one particle.
So
it might have 2 particles in it. But then there's a question of, you just have to go through and do it, right?
So it's not restricted to H1?
It is not.
Okay.
This acts on the whole Fock space.
Okay.
Okay, so this is a good question. This operator acts on the full Fock space. It's not restricted to the subspace of the Fock space that has only one particle. Now, of course, it only looks at the one particle part of it, and you would then have to look at all the, it would depend on the inner products.
Sure.
Right? It's a good exercise. Try it. But now let's define let's generalize to think about the case where we have say a 2-body operator. Yep.
And is there any sense of defining operators with just with just one A and A dagger, or?
Sure, we just did. There they are, A and A dagger.
Ah,
They're
okay.
creating an annihilate.
Yeah, so they would create these states.
They create and annihilate
Okay,
things,
sure.
but they're not promotions
Yeah, okay.
of operators on H2. They are operators on the Fox space, but
Sure.
they're not promotions of any, one body operator. They all have this. Okay. This conserves the number of particles, right? This commutes
With that.
with the total number
Yeah.
operator. It annihilates the particle in this, but it creates it back in that. So no particles are gained or lost or harmed in the making of this equation. Right. Very good. Okay, so now one body's no fun, two bodies. So now I have some two-body operator like the kind I wrote over there. Now, I have to think about, basis states. So if I have some two-body operator, right, this, so it has, our basis are in the product, in the case where I had distinguishable particles, my basis states I could think of as tensor products of bases. Now they have to be symmetrized, right? So they'll look like something like 1 over 2 factorial, in that case it's 2, sum over I and j, I prime and j prime, ei, ej, sum over all these guys, e prime, j prime, e prime, j prime. And this is my bigger matrix that's indexed by 2 things. This would be like up, 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 down, down, up, things like that, for example. Okay? And so this is now I promote to this. So this is my first quantization. And now in second quantization, big O is equal to a half sum over all these guys, ij, I prime, j prime. Now in this guy, I annihilate particle in I prime and j prime, and I create it in this. So it would be O, I prime, j prime, dagger I, a dagger j, a I prime, a j prime. So this is a 2-body operator, involves 2 particles. Okay, again, it conserves the total number of particles. And often you might look at such a term in the following way to kind of Feynman diagram picture. You can think about this as there were 2 particles coming in, one in the state I, the other in the state j, or in this case I prime and j prime. They interact and they go out as particles I and j, where there's an interaction O, I, j, I prime, j prime. Okay, so this is, let me draw things slightly different. Make these guys, particle coming in, the particle coming in, and then the particle going out. With an interaction between them. Okay. So this is a 2-body operator involving 2 particles. Whereas this was a 1-body operator involving 1 particle that, in some sense, scattered from state I into state J through something. lots of things to do. But then I guess we'll do this. So let's talk now about, let's suppose we consider infinite dimensional H. Okay? So this represents, say, a particle moving in three-dimensional space. And generally, I would have this with some spin, right? So those would be, that's the Hilbert space that we've written in standard wave mechanics, supplemented by the fact that it's a spinner, right? I could have a wave function for each spin component, okay? So let's think about that. It's very, very important in thinking about the many-body problem and thinking about the fact that, of course, there are orbitals associated with the motion of those particles. So let's just, to start, let's just consider spin zero. We'll come back to the spin issue, right? Spin zero, these are obviously the bosons. So I can just forget about this for the moment, come back to it. All right, well, so now one of the things we know about this problem is that we have sort of the improper bases of position and momentum. Right? They're improper because you can't normalize them, but they still form, they're duals actually. The only thing that really exists, we can write representations with respect to these spaces. You know, they have the usual inner product. Of course, the momentum eigenfunctions in the position representation are
E to the I, P dot x over H bar.
P dot x over H bar, thank you. And then usually we normalize them with this normalization. So we put in the 2i, the 3 halves over 2. And then they have this normalization. Okay, they're plane waves, and vice versa. All right, that's nice. So I can define, so now P is a continuous variable, and X is a continuous variable. But that's fine. I can now define, say, creation operators in the state that are now continuous functions of P, as what I meant as I created a particle in the eigenstate P. Okay. And we choose, for reasons that will become clear in a moment, for the case of the position, we call it psi. So psi of x creation, it creates a particle at the position x. Okay? It's just a different function. We just instead of calling it a, traditionally we call it psi, for reasons that don't become clear. And of course, the adjoint is the annihilation operator, which annihilates the particle at position x. Okay. And we have then the following. annihilation operators always commute with one another, and the creation operators, these are bosons in this case. But the creation and annihilation operators don't commute with one another generally. What is their commutator?
Delta function.
Their delta function, right? Because this is a shorthand for annihilate a particle at position x, commuted with create a particle at position x, right? And this, by the general rule, is the inner product, which is the delta function. So of course, these things have units. These are not dimensionless operators anymore in the continuous variable. They have the dimensions of the square root of either 1 over position or momentum, right? And similarly, this. And what is the commutator of this with this?
E to the I, P dot X.
Yeah, X. Range bar. Yeah. So, psi is an example, is a quantum field. What I mean by that, a field is a continuous function of position. It's a quantum field because it's a quantum valued. Okay. It is what we might call the second quantized wave function. This is where the term, so where we originally had wave functions as functions, functions now become operators. This is where the term second quantization becomes. It's like we quantize the wave function itself so that the wave function is now an operator. It's a little bit of a weird thing. This isn't really the wave function, it's the creation operator or the annihilation operator, but it's got some intimate relation to the wave function. So let me explain where that relation comes from.
Good.
Before I do that, I guess I should say, let's just generalize this to include the spin degrees of freedom. Bless you. So, including spin, a possible basis we might have is position and the spin. That's a basis, right? Now, often we just, instead of writing this out, we give this some label and call it sigma. Right? It could be up or down for spin 1/2, or all the different n levels for a different spin, okay? Then we define a spinner field with different components, which is just a shorthand for create a particle in this state. Okay. That's so this creates or annihilates a particle in this spin state at that position. And similarly for and then we have the following relations. For either bosons or fermions, the following is true. So these annihilation operators associated with these things either commute or anti-commute, depending upon whether they're bosons or fermions. No, 0. And the annihilation operator and the creation operator, their commutator or anti-commutator is what? What is the answer?
Chronic or delta sigma, sigma prime times the delta
Right,
function.
so it's a Kronecker delta here and a Dirac delta here. Yeah. Stephen, you have a question?
Just really, you may get to it in the next line or two, but what happens if one are primed and the other's not primed? Like you have psi of sigma x on psi.
If this is
that
not a
sigma,
prime?
yeah.
If x equals x prime, then this blows up. Because if x equals x prime, then it's a delta function at 0. So that would be bad.
And yes, there's dagger missing on the secretary.
Here, yes, thank you. Yeah. All right, so let's look at wave functions. So, oh, I guess before I do that, I wanted to just, in the same way that we changed basis back there in that corner where we went from the E basis to the F basis, we can change from the position basis to the momentum basis or vice versa. So, you know, we have in this case our completeness relations look like this, right? Over the continuous variables. So, let's forget, again, for the moment, I just where the spin degree of freedom is just not really the point I want to care about. Call spin 0, but this you could put the spin in afterwards. This creation operator or annihilation operator is equal to or integral to according to the rule that we had before, right? That's how we change basis. what is this? The plane wave. So this says that the field operator x is a superposition, in this case an integral, of plane waves. That's the field operator. Written relates the momentum annihilation operators to the position annihilation, or vice versa. This is a kind of form we see all the time. Okay? And this is why we kind of, again, call this second quantization. I mean, this in wave function language, we would say, this is the momentum space wave function, this is the position space wave function, this is the transfer between them is a Fourier transfer. But now, what we're wave functions are operators. So we re-quantize them, we second quantize them. But we didn't really quantize anything, we just promoted this to a Fock space. All right, so wave functions. So in first quantization, if I had a state psi, then the wave function associated with that is nothing more than the position representation of the state. So redone from day 3, maybe 7, I don't remember when we did that, but it was early on. Okay, what about second quantization? Right, so now my state is, for example, if it's a one-body state, I obtained it by that. Okay? And my x is obtained by that. Okay. So my wave function, still this representation, but that is this. That is the wave function. Let's double check. Right? So what I've done is I look at the annihilation of the state at the position x, and I look at the projection onto the vacuum. That is the single body wave function. And again, it doesn't matter that whether this was a one body state or not, but I'm just comparing it for the case where it is. So let's just look at this case. So this is equal to a dagger, right? And what's that? What's the trick? You flip it, right? And you add in the commutator, the anti-commutator. So this is equal to, since it doesn't matter because it annihilates it, in this case they're bosons. And that is what? It's the inner product of x with that. Yay! So it works. That is the wave function. The wave function is this thing. That's the one body wave function. But suppose we had two bodies, and I wanted to know, if they don't end at 1050 something, it's not actually the last class of this list. So now I have let's say I have the two-body state. Okay? First quantization. My wave function function associated with the joint probability amplitude of finding it here and here is equal to that, right? No, not squared. That's the probability. It's this. Right? So that's my wave function, the two-body wave function. Okay? So now, let's say that psi of x1 and x2, for example, is one particle is in state phi A, and the other is in state phi B. Of course, I don't know whether particle 1 is in A or B. Right? So I have to assume that's the first quantization version of the two-particle wave function. Now let's go to the second quantization. So my state here is create one particle in A and the other particle in B. And let's just suppose, since I don't want to have to renormalize things, that these are orthogonal states. I don't have to, but then I have to renormalize it. I don't want to. Okay? Okay? And my x1, x2 is, I have to, over 2 factorial, dagger x1, x2. So now I conclude to calculate what is the wave function of the two particles. It's equal to 1 over root 2, 0, annihilate, A dagger A dagger B vacuum. Right? So this was the state. I created a particle in orbital A, created a particle in orbital B, and this is my position K. Right? Okay, how am I going to do that? Well, I gotta sort of sequentially commute this through or anti-commute it through if these were fermions. Right? So this is going to be equal to 1 over root 2 x1 commutator x2 dagger A plus them in the other order. So I just flipped these and added the commutator. If they were fermions, I would have put a minus sign. This would have been the anti-commutator. Okay? Let's do that. Let's pretend these are, I put on the spin thing, they're bosons. They're all in the same spin state, but they could be bosons and fermions. So let's be fun and put in that. Okay? So now this is equal to what? Well, I commuted an annihilation with the creation numbers. The inner product of this with that, that's x2 by A. It's the wave function associated with orbital A. And then I do the same thing here. And I'm going to get I switch the order. It gives me another commutator. That will give me x1. And when it's all said and done, it's a little exercise for you. This would be phi A x2 phi b x1 plus or minus for bosons or fermions in the same spin state phi a x1 b. Yay! so that's the beauty of this. We don't have to deal with putting all the orbitals and putting it on. It's done. And this is clearly not an entangled state with respect to that. It's just a product state of sorts, even though it kind of looks entangled with respect to that. All right, folks. There is, of course, a lot more to say, and I think I'll see what you guys are in the mood for next week, and I think we'll conclude for now. I would encourage you, if you're interested, and I think you should be interested, to take quantum optics next year. Because we're going to be continuing a lot of this fundamentals of quantum mechanics there. It's a forum for us to really think about the foundation of quantum mechanics. And we'll be picking up pretty much right here where we left off, talking about quantum field theory, which is sort of the reverse. Here we went from particles to fields. Quantum field theory goes from fields to particles to make some connections between them. All right. It was a good semester. Think about it whether you want to take the final. Happy to discuss it with you. If I don't see you, have a great summer.